Good afternoon, everybody. What we wanted to talk about today, or what we wanted to present or show you today, is a small piece of the oranges and lemons project, which, to be honest with you, we didn't really sort of give it very much attention, simply because I suppose we took it for granted in a way. But thinking about it, it's a piece which, although it was very much in the shadow of the polarimeter, this was a piece which was actually quite fundamental to the project and to the aims of that project, which were to explore limonene, okay, as a molecule. Now, what we want to try and get across today, though, is that the limonene project is really just a pretext. It's just an excuse, and what we have in essence is let's say an experience which is potentially much wider and much broader than just that particular project. So, as Daniela said, we're going to talk about the black box colorimeter, and I'm going to start with. Okay, so the aim of this workshop is it's actually very simple. I want to try and convince you, and particularly for those of you who are physics phobic and electronics phobic, and who get scared by the simple mention of resistors and LEDs and wires and stuff. I want to try to get across to you that you can do this type of project with a little bit of patience, a little bit of logic, because you have to think through some things, but you do not have to be one of these guys, a maker who is sort of deeply into robotics and stuff to get something, let's say, positive from this experience. Okay, now the thing about this little project is that there is a part where you're making an instrument, and then there's a part where you're using it. And we use this to introduce the concepts behind the Beer-Lambert law. Typically, this is something which you will encounter later on in the school curriculum, so fourth year, fifth year. And sometimes, let's say, the actual, let's say, application of this can be a little bit confusing for students, simply because it sort of happens typically in two steps. So what we're going to do now is we're going to show how you can use this very simple instrument to even make measurements which, okay, we're not talking professional analytical chemistry level precision, but which certainly are able to demonstrate a principle, and which are an experience which is able to actually calculate things, to get numbers, to do some quantitative work. Okay, so this is the example from the oranges and lemons project. You can see there's a distinct change in the when we react the double bonds in the molecule that we had, the limonene molecule, with permanganate, and there's a clear color change from purple to pale yellow, colorless. Okay, so the whole point is to be able to estimate the amount of permanganate that you've used and work backwards to estimate the amount of limonene that you've got. That was the idea of how this was used in this particular project. But of course, this is something which could be applied to many different chemical reactions where you have a change of color. So the idea is that the amount of color can give you an indication of the concentration, the amount of stuff that you actually have in your test tube. So the Beer-Lambert law itself is relatively, let's say, it's relatively straightforward. But I just wanted to make a couple of comments about this, because, of course, if you have light passing through a solution, you can measure how much light actually comes through or how much light doesn't get through. And the first is transmission and the second is absorbance. And basically what we tend to use is the absorbance as a measure, simply because it has a linear relationship with the concentration of material in the solution. Okay, so whereas the transmission has if I remember correctly, it's a log type of relationship, which makes the, let's say, the calculations a little bit more complicated. So what we typically do is we typically measure the absorbance as a function of concentration. Now, we've got these two other terms here, which this is a proportionality constant, which depends on the stuff that you've got in the solution. Okay, to do the work that we're going to propose today, you don't need to know this. Okay, and you'll see why in a minute. This is an L. It's a path length. Okay, so if you have a colored solution, you can imagine that intuitively, you know that if the light is passing through more solution, less light will get through, so more light will be absorbed. So what we typically do in these cases is we fix this as it's typically defined as 1 centimeter. Okay, simply because it's convenient. Okay, and you'll see that in a minute when we look at the actual instrumentation. So what we have is this direct proportionality, which we can use to our advantage. Now, basically what we can do is if we're wanting to try and find a concentration of an unknown solution. Okay, so let's imagine we have a colored solution, whatever color you want, red, blue, whatever, and you have let's say you have a situation where you don't know exactly how much stuff is in there. This was our situation with the limonene, if you like. What you can do is you can take solutions of the color which are known concentration, and create what's called a standard curve. And basically what you can do is you can create this, let's say, this graphical relationship, which then allows you to go backwards and find, based on the absorbance, find a concentration for that absorbance. Okay, now obviously this does rely on a linear relationship. This is data which I did the other day, and I'll show you the solutions in a minute. It may look a bit wobbly, but I'm looking at I use Excel, or we used Excel to calculate the regression coefficient to give us a guide as to how good this data is. And it's pretty good, considering the simplicity of the materials and the instrumentation. Okay, so let's have a look. So the photometer. So as I say, don't fear the circuit. Some of you may be old enough to remember Blue Oyster Cult and Don't Fear the Reaper. Well, here this is Don't Fear the Circuit. So this is the beast. Okay, now it's a black box. Okay, and we've got a readout, and we've got some stuff now. I don't know whether you can actually see in. Oh yeah, there you can see it. Okay, so that's my. Okay, it's changing. It's changing color. Okay, and I can, if I wish, but I'm not going to do it here because it's not so exciting. I can change the intensity too. Now I can imagine you're already thinking, no, this looks a bit too complicated. Okay, well, I'm going to try to show you that actually you can make a version of this, which is, let's say, the stripped down version, which is a lot simpler. Okay, now Francesca's husband made this for us because he's one of those guys who just sticks circuits onto everything. So he's really good with that sort of stuff. Having said that, there is the possibility of making a much simpler version. So what have we got in the box? Well, we've got quite simply a light source, and as you noticed, the light source was a particular color, so it's monochromatic. We have a power supply, of course, because it's a circuit, and we have some way of measuring the amount of light which is passing through a sample. Now this, you can see this thing here, this is a cuvette. Okay, obviously this is where we put the sample. It's 1 centimeter by 1 centimeter. Okay, and so that obviously will just fit into here. Okay, make sure you put there's a zigzag side and there's a plain side. Put the plain side so that the light will pass through it. Okay, you put a top on it, take your measurements, easy peasy. Okay, so let's have a look at where we can take this. So this looks complicated for anyone who's not into electronics, and I'm not into electronics, honestly, really. I can just about wire a plug. It looks a bit complicated, but why? Well, simply because we have the possibility of selecting intensity, we have the possibility of changing colors. Okay, there is a let's say a stripped down version, which I'll show you in a minute. But basically, let's just have a look a little bit more detail at how the thing works. Basically, when you are using LEDs, okay, which are cheap as chips, when you're using LEDs, you always have to use a resistor, because the LEDs can only take a certain voltage, okay, and they'll only take a certain current. That might be the thing you need to play around with, but there is a link in these slides which takes you to a place where you can do the calculations, but it really is not difficult. Okay, so you need some resistances, and if you're going to modify the intensity, you need some more resistances. So that's basically this, let's say, this particular setup. Okay, so what's inside the black box? So 9-volt power supply, LEDs, there will be a resistor here. Now, one of the criticisms that people may make of simple instruments is that you don't have good resolution, you don't have good, let's say, you can't do much with them. Well, that's okay, it's true, but what I'd like to sort of suggest is that actually these days, with the LEDs that we have, and you can get different colors. These LEDs typically have a very narrow bandwidth in terms of the light which is produced, and so they're actually pretty good as monochromatic sources. The alternative, which is not fantastic, but it does work, is to use a white light source and filters, colored filters, the sorts of filters that you'd use in photography. But these days, the LEDs are so cheap, so easily available that there's really no excuse not to use them. Okay, so the next, let's say, the next part is the sensor and the measurement system. So the sensor is simply a photoresistor. And again, you say, oh, photoresistor, it sounds complicated. No, it's not. It's just basically a resistance which you shine light on it and it changes its physical properties so that it lets through more or less current according to how much light is being shone on the thing. So as far as the readout is concerned, now in our, let's say, black box version, the readout is with 3 decimal place LED readout. However, you can actually get away with just a voltameter, and I'm going to show you this in a minute. So it can be you can really sort of reduce all of this to a really sort of bare bones, essential thing. Okay, so the cuvette with your sample goes between the LED and the resistor. Cuvettes themselves, once upon a time, it was all stuff professional laboratories and what have you. But now, well, you can get them, again, they're cheap as chips. You can get them from Jeff for about 17 euros for a box of 100. And if you clean them, they last for ages. Okay, so as you sort of increase the concentration of material, you will get the absorption. This is a very simple plot of potassium permanganate at different concentrations against, the voltage against a potassium permanganate concentration. Okay, and quite simply, as the solution gets more and more concentrated, we build up the line. Okay, now these are real numbers. This is real data from our black box. And again, what am I looking for? I'm looking for a good R squared. These numbers are really sort of quite ridiculously exceptional because it's 1 essentially. So yes, we have a nice linear relationship. Now this is the voltage, but the voltage is not the absorbance, of course. So I'll come to the okay, right. The question is which lead for the potassium permanganate. Okay, so that's to do with the absorption. And to get the maximum effect of the absorption, you use the complementary color. In the case of potassium permanganate, you would use something like an orange color because it's purple. Okay, it might be orange yellow. Okay, you will not be able to get hold of the exact, let's say, the exact LED for the exact color shade, but you will be able to get close enough. Okay, so this is now the stripped down version, and I'm going to let me just Okay, so I'm just going to show you this live, actually. So it's clear this is made of Lego. Okay, so no children were abused during this, the making of this, by taking their toys away from them, because this Lego is actually mine. Okay, so let me just sort of show this very, very simple thing here. This is the photoresistor. Okay, so I've just put it in here on this side. Oops, let me just take this out a minute. On this side, we've got the LED. I'll just light it up so you can take it for. You can see the LED is working in there. In this case, this is an orange one. Okay, now I've got some bits of paper in here, bits of black paper, just to make. Oops, go on. Here you go. Just to make the box as black or as dark as possible. Okay, so I'm just sort of assembling this up here, and the whole thing is relatively straightforward. Okay, now what I've got here is I'll just try and show you this bit here. This might be a bit more difficult to, yeah, there it is. That's the resistor. Now, as I said, don't fear the circuit. I'm not doing it. I haven't done any soldering here. So quite possibly someone would say, oh yeah, you're going to have resistance and stuff, which you do have, because you've got imperfect contact. But for, let's say, for a very, very basic attempt at this, these connectors, which are electricians' connectors, work fine, okay, without too much fiddling around. Because once you start soldering stuff, that's when it gets a bit too much for many people. Okay, so what I've tried to do here is I've tried to make this resemble, let's say, this is a bit difficult to see here. I tried to make it resemble as much as I can, oops, that way, the circuit. Now I'll show you, I'll go back to the circuit diagram a minute. And what we've got, is we've got very simply a battery. The resistance, that's this resistor. I'll tell you what, right, okay. So that's that resistor, which is here. Okay, so I'm doing this with my left hand, which is not a great idea. There we go. Okay. So this yellow cable, which is coming off here, okay, this is going to be coming to this part of the voltameter. Okay. The rest of the circuit comes around and it basically connects to the photoresistor. So using sort of this setup, and here's my here's my voltmeter. Okay, which my able assistant. Okay. Okay. Basically, what I'm going to do is I'm just going to put you can see that the voltage is changing. Okay, now of course here I'm going to have to put a sample in. So I've made this special little cardboard holder. Just takes about 3 seconds to make. Okay, just to make it just 2 seconds. Just decided to not. Okay, right, now let's just see. Okay, so you can see there's a change in voltage. Now this is just water. If I turn it around, I'm blocking a lot of the current. You can see the voltage is falling. This is basically, I've blocked the light, so I'm going to get the current which is flowing through the resistor when there is no light, and this is very important for the calculations. Okay, so just to repeat, a very, very simple box. Lego is extremely useful for all sorts of stuff. because you can drill holes in it, and that's what I did to get the resistor in there, to get the LED in there. The whole thing, well, cost is, I don't know, it's a few euros basically. The resistors and the LEDs are really sort of very, very cheap. So the voltage plot is relatively straightforward, and that demonstrates the linearity of the relationship. However, if you want to do the absorbance, then you have to do this, okay? For some people, this might look a little bit scary, but it's not really so difficult. You just have to keep your head about you. So what we're looking for, this is what we're going to measure, the voltage in the sample. We also measure this, which is, in this case, it says water. This is the solvent that we're in the solution that we're using in the solutions. This is the dark current. What does this mean? It means that when there is current flowing through the circuit, but no light at all is hitting the resistor, there will be a current through the resistor. So we need to measure that voltage. Okay, so we do that simply by covering the light source, covering the resistor. Okay, so just to give you the sorts of results that you can get, and as I say, this really is very, very simple. In this case, let me just demonstrate let me just show you the. I got some blue food dye from the supermarket. Now, why people would want to make blue cakes, I've got no idea, but some people do. And so what I did was I took, oops, not that, this one, it's this one. I took the food dye solution, which is a small, quite concentrated solution, and I diluted it to 10 milliliters with water. I used that as my 100%. Now, I don't know how much food dye there is in there, because it doesn't say on the bottle what the concentration is. So I'm using percentages here. That's my 100%. And then, of course, you just do a serial dilution. So you take 8 milliliters, 6 milliliters, 4 milliliters, 2 milliliters, and just make it up to 10 with water. Okay, so it's a very, 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 very simple, experiment. And well, you do the calculations. So these are the observed voltages. These are the voltages for the solvent, which is the water, the dark current, okay, the dark voltage, and the solvent minus the zero. And basically, just do this in Excel, stepwise calculation, and you get to an estimate of the absorbance. Okay, as you can see, the relationship is linear. It's a nice straight line, and this is extremely reliable. You have to just be careful with the batteries, but it works every time. Okay, you can, if you have solutions which are known, then you can do more interesting stuff, like like estimating the amount of materials. For example, we used it for the permanganate. You've got some, let's say, you have to be careful in some respect, because if you have solutions which are too concentrated, you may find yourself in a non-linear part of the response curve of the resistor. Okay, so as I say, I took the sample from the supermarket, and it was really quite dark blue, and I thought, no, this will almost certainly be too much. But again, this can be part of playing with the conditions of measurement, because the resistor will have a certain, or the system will have a certain, let's say, range above which it's nonlinear, and below which you have no resolution, you can't detect. Okay, so obviously, if you're talking about really sort of quite weak solutions, you may not see much. So you have to play around with this sometimes, okay, with a little bit. Okay, so I've sort of mentioned the thing about the photoresistors and their linearity. It will depend on the resistor. Some will be better than others. It will depend on the quality. So this is something that you just have to play with and find out. Okay, you may have problems with extraneous light. So one of the key things is to just, well, one of the easy solutions is to just put everything under a box or a blanket and take the measurements. Okay. You'll need a cuvette, although as Bob suggests, you could try with Tic Tac boxes after you've eaten the Tic Tacs. That might be interesting, actually, because with a Tic Tac box, you have a rectangle, so you can have two different path lengths. That will be interesting to see the difference there. And of course, as I say, the batteries. You need to be, since this is battery run, you need to be aware of the batteries. Okay. Okay, yeah, Bob just said that he did do the he did do the Tic Tac box inversion. I don't know whether it's possible, whether they make bigger boxes or not, but yeah. Okay, so, and then the last thing is the choice of the resistor. Oh yes, they do. It sounds like you're a Tic Tac fanatic, Bob. Yeah, so the other thing is the choice of the resistor. That will depend on your lead, and you'll get that from the information sheet which they give with the product. So you'd have to do a slight calculation, but if you follow this link, it will guide you as to how to make that calculation. It really is not particularly difficult. And so, as I say, the whole thing here is to take this, because for physics teachers, this is sort of fairly normal stuff. But if you're not a physics teacher, but you want to do something a little bit more fancy, maybe you see a circuit diagram and you go, no, I can't do that. Okay, so just don't, as I say, don't fear the circuit. Okay, applications. sorry. So one of the obvious I've mentioned several times, the idea of the concentrations, unknowns, measuring unknowns. Okay. What about kinetics? Well, this is obviously something which really lends itself to kinetics measurements, and for example, the reactions of blue food dye with bleach. Okay, and you can monitor the change in absorbance. Anyway, so the thing is, kinetics is obviously something which is lends itself very well where you have a change of color. If you have the situation where you don't get a colorless solution at the end of the reaction, of course, what you would have to do is you would have to set up a situation where the reaction goes to completion and measure the final volume. The final voltage, which would be like your background. Okay. Right. I think. Yes, that's it. Now, just a comment here, because obviously there are quite a few versions of this out there on the web, and it's not particularly new. But that wasn't really the point of this webinar. The point of this webinar was to sort of persuade non-physics teachers that it's perfectly doable. Okay. The original idea for this, for me, came from this article here, which you can find on the RSC, the Royal Society of Chemistry website, which is build your own spectrophotometer. Now, this one is a bit more complicated, and you have an operational amplifier, and you have a slightly more complicated circuit, and it's a bit trickier. So this was where a conversation with Francesca's husband sort of cleared everything up. He says, "Oh no, you don't need all of that stuff. Just do it like this," which is fine. Okay. So for the simple, let's say for the simple version, which as I've demonstrated, for the simple version, it's perfectly reasonable to avoid all of the electronic stuff that this article talks about. But this is well worth doing if you have the patience to do it. Okay. Another article which I think is worth looking at is, and this is sort of linked to Bob's Tic Tac boxes. It's the idea of the investigation of the path length. Now, typically when we do Beer-Lambert stuff, we don't usually use we concentrate on the concentration and just ignore the path length, because the cuvettes are always 10 by 10 millimeters. Okay, except in certain situations. So this setup is interesting because it allows you to actually vary the path length. So it's an interesting article, this one. Okay, thank you everybody for your patience. I hope, as I say, I hope you've enjoyed this this short workshop. So have a good evening, and thank you very much.